All right, we are back, and we are about to do our P-Set 2 basically solution videos. All right, so identify what type of conventional unit cell is present in A through C. So we know that this is simple cubic. We know this is FCC. We know this is BCC. So we got that. Number of atoms, 1, 4, 2. Got it. Number of nearest neighbors. This will be 6. This will be 12. This will be 8. So number of nearest neighbors, boom. Nearest neighbor distance is always 2r. Got that. Lattice parameter. So this is 2r here. This is 2r square root 2. This is 4r square root of 3 for my lattice parameter. Next nearest neighbor distance. So the next nearest neighbor distance for here is 2r square root 2. This is my next nearest neighbor distance. This is my next nearest neighbor distance as well. Atomic packing factor. Not close packed, not close packed. That APF is about 0.74, and we've done that from our notes. Are any of these cells primitive? A is primitive. Got it. All right, now let's look at directions. So let me erase everything here. Let's delete it. So let's look at naming our directions. So let's start with here. So where's our finish? So our finish point is at 1, 1/2. And that's going to be 1 minus our start, which is going to be 0, 0, 1, which is going to be equal to what? So we're going to do minus a hat. We're going to do, actually, excuse me. So we're going to do, it'll be 1, 1/2, 0, and then we know that that has to go to 2, 1, 0. So there we go. That's this one done. What about this guy? So our finish is 1/2, 0, 0 minus our start, which is 1, 1, 0. So that's going to lead to minus a half. 0 minus 1 is minus 1, and 0. So that leads to, not 2, excuse me, 1/2, 2/2, 0. So we've got that one done as well. What about this guy over here? So my finish is at 1/2, basically 1, 0, minus my start, which is at 1, 0, 1. So 1/2 that, so I'm going to have that's going to be a minus 1 eventually. So 1 minus 0, that's going to be a 2. And then a 0 minus 1 is going to be a 2/2 here. There we go. And finally this one, where are we going? Let's delete this one here. We have my finish is at 0, 1/2, 0, minus my start, which is at 0, 1, 1. So again, what is that going to leave me with? It's going to leave me with a 0. It's going to leave me with a minus 1, and then it's going to leave me with a minus 2. There we go. We got it. So those are all my directions. Are any of these close packed? No, because we know that our close packed directions are of the 1, 0, 0 family. So for A, our close packed directions are of this variety, and we didn't have any of those. Excellent. Let's identify the crystallographic planes. So I need to change my origin. My origin is now going to be here and here. So what are my intercepts? My intercepts are at x equals 1. My y-intercept is at minus 1, and my z-intercept is at 1/2. So I need to flip these. So my plane will be 1, 1/2. Flip that, 2. Voila, got it. What about here? I'm going to do the same thing. Choose my origin here, and then I'm going to go, where does it intercept here? My x-intercept is going to be at 1/2. My y-intercept is equal to minus 1. Where's my z-intercept? Z is equal to infinity. I'm going to flip that. So I'm going to have 2, 1/2, 0. Got it. Fantastic. Did it indicate your origin? Did that? Are any planes close packed? Well, this is not of the 1, 1, 1 variety, so it is not. There's no close packed planes in C. Indicate the close packed planes for A and C. A and C, there's none. So that's our effective answer. Calculate the planar density quantitatively for the plane in C. All right, let's go ahead and calculate this one out. So what we have here is a plane like this, and we're not passing through that center. So we have an atom here, we have an atom here, and that is effectively it. Now, technically speaking, if we kind of continue that plane, we'll hit those other ones, but let's kind of ignore that for now. So we know that this is A, and this is going to be A square root of 2. So my planar density, I need my number of atoms, which is, each of these is a quarter contribution, because there's going to be 4 planes sharing it. So I'm going to have a half an atom times pi r squared divided by A times A square root of 2, where A in this problem is going to be equal to 4r over square root of 3. So that's kind of the key thing that we needed to do here. So let's pull up and let's quit our kernel here. Let's go ahead and see, actually, right. So A is equal to 4 times R, oops. A is equal to 4 times R divided by square root of 3. So that's my A, and I need to do 1/2 times pi times R squared. I want the whole thing, probably redundant, but that's my choice. A times square root of 2. Area of my plane. And let's look at this numerically. Is this a closed packed plane? Definitely not. All right, got it. So let's look a bit closer. So draw an FCC cell in D. So we'll go ahead and draw that. FCC, boom, 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 face, 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 face. What about the 1 minus 2 direction? So how can we draw that direction? Well, let's actually calculate it out first. And actually, to do that, let me kind of give myself some space here again. So let's delete that. So if I want to do minus 1, so I need something like this. Finish minus start. So I need something where it's 0 and 1 here. I need something that's, for example, 1/2 and 1 here. And let's just do 0, 0. So I could have something where my finish arrow is right here. And then I could have my start, so like that. And I could have my start be 1, 0, 1. So I can go here. Yeah, let me get in here a little bit. So I can go from here to here. So there we go. Let me zoom out a little bit. So we've done that direction, and it is a direction because it has this. Is it close packed? Definitely not. Remember, what are our close packed directions here? They're going to be the 1, 1, 0 directions. Now let's draw this plane here. And actually, we can do that. What are our intercepts? X equals 1, Y equals 1/2, and Z equals minus 1/2. So I know, and actually I'm just going to kind of erase this just so we can kind of see. I need my origin to be higher. And I need it to be, actually, because I'm going to go positive, positive, I'm going to choose my origin here. So here's my x-intercept. Here's my y-intercept right here. My z-intercept is minus 1/2. Boom, boom, boom. There we go. Calculate the planar density of this plane quantitatively. So that's where we need our... so we're going to go here, here. So there's no atoms here, but there is an atom in the face, but it doesn't interact. So I have, basically, I'm going to have an atom just right to here. And we know that that is a 6. So let's go ahead and calculate that one. So we know each of these quarters is a 6th. We know that the area basically here, but actually, are we at an equilateral triangle? Let's go ahead and look at that here. So we're going to have not really the same length here. But basically, this is going to be, in our equation, it's going to be 6. We're going to have that square root 3 over 4 x squared, where that distance, actually that distance should be the same. So we'd have to actually calculate that distance out, but it will not be close packed. Excellent. So let's go ahead and draw the following directions in the unit cell. So I'm going to go ahead and do, let's just do in order. So I'm going to do again a 1/2, a 1/2 1, a 1, and a 0, or actually, excuse me, because we're going to be multiplying this. So actually, excuse me. Actually, let me recheck my answer up here on the basically the 102. So the 102, that had to be basically a half. I think I did that one right. 1. There you go. All right. Just double checking. Sometimes. All right. 0 minus 1. Excellent. That has to be a half. Good. And then this has to be 1 and a 0. How about 1, 1, 0? So that's going to be pretty nice. So I could finish 1, 0, 0, 1, and you can just do 0, 0. I think that'll work. And then finally 2, 3, 2. So now we're going to have a basically a 6 thrown in here. So basically 1/3. We'll multiply everything by 3. 1/3 will be exactly. And so 2/3. Let's figure this one out. All right. So first is minus. So minus 2/3. So actually, because if I multiply everything by 3, so yeah, actually, I'll just do. I'll do 1 minus. Actually, I'll do 1/3 minus 1, and then I will do basically 0 minus 1, because that'll give me the 3, and I'll also do another. Here I'll do a 1 minus 1/3, and that should give me what we need. All right, let's draw these. So these are all finish minus start. So start here, and then I need to go to 0, 1/2, 1. So I could do that here. Finish also here. I could do that one, and then 0, 1, 0. So I could do finish there, start here, and then I could do my other start, which is 1, 1, 1/3, and then I could do my finish, which is 1/3, 0, 1, like this. Voila! I think we've got that. Let's just double check. So I do minus 2/3. I would be minus 1, and then I'd have 2/3. Multiply everything out. Good. Ready to go. 6 is done. 7. In this empty unit cell, which will become empty now with the stroke of my pen quite easily, draw the 0, 0, 2, 2. So again, so we're infinite here. So our intercepts, our y is equal to 1/2. But we need to change our origin because our z is here. So let's go ahead and choose our origin here. So no intercept here. My y-intercept is going to be 1/2, and my z-intercept is going to be negative 1/2 here. And I could choose, let's choose my origin right here. So x, y, so it'd be the same thing here. And then, and then my origin would be minus 1/2 here. So actually I could go here, here. I could do cross that. So something like that. So, because if I look at it, 1/2 minus 2, minus 1, 1/2. 1/2 minus 1/2. So that would be my plane. What about the 1, 3 minus 2? So again, we need a negative, so we're going to have to go basically to the left here. So let's choose our origin as such. So intersect here, minus 1/3 right here, and then 2, which is going to be 1/2 right here. Boom, 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 and we got it. Triangle. Fantastic. On to the last one. So now we're looking at a material or PDF like this. So we know that this is a metal. I know that 2.82 is my nearest neighbor distance. So if I look at, so let's go ahead and look at it here. So my atomic radii, or my R naught, is going to be 2.82 angstroms divided by 2, 1.41. And then if I look at, because remember, my second nearest neighbor distance is either 2 times R times square root of 2, excuse me, divided by 2 times R, divided by 2 times R. So let's look at that. 3.26 divided by 2.82. So it's probably not that one. So our other ratio is 4 times R divided by square root of 3. Voila! Good. So pretty close. 2.82, 3.26. So this looks like a BCC material. So it's going to have the integral of this peak should be 8. So it should be BCC material with an atomic radii of 1.41. And let's go ahead and look up our values here. BCC, cubic bonding centered, is right at the center there, so that's slash. So I don't see any here, but we should go over the other side. We should go over here, but I don't see. Actually, we can just do the trick my students taught me. 1.41. Let's look at it. So gallium's not going to work. Nope. Nope. Where's our next one? Ah, tungsten. There it is. That's our value. So we are working with tungsten. We know the nearest neighbor distance. What is the next nearest neighbor distance? We know that. We already used that to solve. Integral of the first peak. We've got it. Awesome. And that is it. P-Set 2 is done. So hopefully you've done well, and we'll see you all in the next video. Thanks. Bye.